about this fact that, okay, if we assume that the language model is super capable of doing things, like we have trained a very, very good language model which is capable of completing a sentence perfectly, then essentially if we want to just do one specific task, maybe we can play with the kind of prompt we are giving, with the kind of input we are giving to this language model, right? So you remember this example which we started with. So the funny example of how you can get rid of Ali Brahe, which you can never get rid of me. But if you wanted to answer this question, then fine-tuning was the idea to get a couple of those question answers, and then you keep training your model, right? But when we think about prompting, we actually ask this question. We say, okay, if this is the question, maybe I can put a bit more context into this question, and then I make this language model to complete the answer, or this token sequence with the answer, giving it no other way to complete it with another completion, right? So the idea was that I just put a bunch of extra tokens, like I put a question mark and then I write, the answer is that you can get rid of Ali Brahe by, and then, well, if it is a perfect language model, meaning that it has been perfectly trained to complete sentence in the most likely way, the only likely way, or the most likely way would say to complete this sentence now is to just give the answer, right? And then it's going to just write the answer right after it. So this was the idea of prompting, right? And we talked about a few things, two basic ideas, which, as I said, they were like original ideas for prompting. And at some point, they were just being used to somehow evaluate the model. So the first one was few-shot learning. And what was the idea of few-shot learning? So we wanted to learn the label of one particular data point, or say I want to give the answer to one specific question, by giving my model a few examples, right? And I somehow incorporate these examples into the form of the input to my model. So what do I mean by that? I mean, in terms of the language model, I have not trained my language model to translate any sentence, right? So my model is essential. It has seen lots of, English and German text, but it has not been specifically trained to translate, right? Now my question is, if it has been a few-shot learner, it means that if I give it enough context, then it starts to somehow understand what kind of task I'm looking for, and then it's able to do that. For instance, I ask explicitly, okay, translate to German. I put one English sentence, the German translation. Next English sentence, next German translation, and so on. And then finally, I put the sentence that I want. So this last sentence is essentially what I was looking for. And then if this model is capable of few-shot learning, then it should essentially give the German translation to that, right? So if it can do this, then this guy is a few-shot learner, right? And at some point, it was the idea that, okay, this is not going to happen all the time because language models are not perfect, right? Or models are limited. But maybe we can try a few examples of that on a newly trained language model. And if it's able to do that, then we're going to report it and would say, okay, our language model is working better than the previous ones because it's doing better few-shot learning. Okay? So at the beginning, this was the original idea. And what people started to see, so this was the idea in GPT-2. So we're talking about the time when GPT-2 was out there. And at that point, what they saw was that if they do accurate prompt design, so if they write these sentences, put these tokens very properly into the input of the language model, then it's able to do a few of those tasks. So this is why they call the paper to be language models are unsupervised multitask learners, because they saw that some of those tasks, by giving a few context in the prompt of the language model, are being done by these language models. Okay, but as I said, at that point of time, people thought like, this is a kind of fancy thing. We only try to examine it to just show how well, to what extent our model can go, right? But nowadays, it's essentially a kind of thing you do it every day with those language models. So quickly, they started to be that thing. Another idea is the zero-shot learning, so again, we talked about it. We want to somehow give a label to an unseen data. And in terms of language models, is again easy to think about that. What do we mean? I mean that I do not give any example of translation. I just say translate it to German, and then I give the English sentence, right? And then that English sentence should be translated to German if the language model is perfect, right? Because if the language model is perfect, it knows, it has seen lots of German and English sentences, right? And then it started to understand how to convert English to German. And then what I'm commanding my language model is basically perfectly completed by that particular German translation, right? So the most likely completion of this sentence is the German translation. Again, this was a kind of idea that people try to just examine at that point of time, and then again, they have seen if they do very accurate design of the prompt, then, well, it can do few of those tasks, right? But then gradually, this became a kind of thing. I mean, GPT-3 was able to do few-shot learning, not zero-shot learning perfectly, but nowadays, I mean, GPT-4 is essentially zero-shot learner, right? So you don't really need to give even an example to that. This whole thing is the idea of prompting or prompt design. The prompt design means that you're getting your input, yeah? So you think of the kind of data you want to map into its label. So you have a question, you want to connect it into the answer. And the whole thing that you need to do, you need to put it in the right context, right? So if you put it in the right context and give it to a very good language model, then it should essentially be able to complete it with the label that you want. In other words, you just give the language model no other choice rather than answering your question, right? So how can I formulate it into the framework that we had up to this point? So let's just think about a general task. So again, if you want to think about an example, always think about question answering, right? So I am giving one prompt, one query to my language model, or any model, and corresponding to that prompt, corresponding to that query, there exists one label y, okay? So u is essentially your question, y is your answer, right? And then this is following one task-specific distribution q, yeah? So what you want, what you would be happy is that you just give the prompt u, and then you get the answer y, right? So sampled from that distribution. All possible fine answer to that question, right? So what you don't want to have an irrelevant answer, right? And what we have in hand to just mimic this kind of distribution, what is the large language model? And our large language model has been fine-tuned, meaning that this LLM W here is your transformer-based language model, that very deep language model. And this W is essentially presenting the weights of that model. So it's able to just get x1 to t, so a sequence, an incomplete sequence of tokens. And then this is able to just sample some extra tokens up to a limit, which completes that sequence, right? And once you have your language model, essentially you know what is the distribution, right? Because your language model, what it does, it looks at the sequence and it starts to compute the probability of the next one and sample from it, right? Again, probability of the next one and sample from it and so on, right? So you have all the probabilities. We talked about it multiple times. So we do know what is the chance of, the completion coming out, right? And then the language model is able to compute this for us, and we have fine-tuned it on a massive amount of data, right? But none of those data was specified for that task, right? Now, the thing that we want to do, we want to just do a prompt design. And what do I mean by doing a prompt design? The prompt design consists of two things. The first thing is the prompt encoding. And by encoding, I simply mean putting your question in the right context, right? So what is the encoding that I did in my dummy example? Instead of just writing the question, I put the question, then I put one question mark, and then I gave a bit of more context, right? The answer to this question is, then I made my language model to answer, right? That question mark and the context I provided, this is essentially the encoding. So I am not just giving my question plainly to my language model, I'm adding context to it, right? So if you want to think about a more general task, and if you want to think about a more general way of prompting from your language model, then you can think of a general function f, right? So this function f is getting the question and put it in some other format, which is now an incomplete sentence for your language model, right? And now I'm going to give this incomplete sentence into my language model. What does my language model do? What does it do? It completes the sequence, right? So you're going to put lots of tokens to finish it, right? Now, you have a longer sequence. This is the completed one. What you want out of this? Your answer, right? So you're going to see at the completion it has done, and then you try to extract your answer from it, right? So in my dummy example again, I said the answer to this question is, and then whatever comes after that is essentially my answer, right? So I'm going to just look at anything after is, and then that is my answer, right? Again, you might think of a more general case, and in a more general case, you can think of a decoding function, which looks at this whole completed sequence, and then takes out the kind of label you're looking for, the answer that you're looking for, right? Okay? So this is the idea of prompt design. I want to design one function which does the encoding and just passes the query to the language model, and another function which does the decoding, taking out my label out of the completion by the language model. Now, what do I want? What kind of behavior do I want to see after doing encoding and decoding? The answer to the question, right? Now, if I give this question, so like if I wanted to translate the sentence, right? The sun shines, right? And I said, I put some encoding. So encoding was translated to German, double dot, then quotation mark, the sun is shining, quotation mark, right? So this was the whole encoding. So I put my English sentence inside that format, right? It went to the language model, it just completed that one. The sentence that is completed, is it necessarily always one sentence? Does your language model always complete it the same way? No, it can give you different outcomes, right? Why it gives you? Because it's just sampling from the distribution, right? And of course, if your distribution is focused on one particular outcome, most of the time that particular outcome going to happen. But it might be that that outcome is not unique, right? So you might sample different forms. And you have seen this in like most LLM, commercial LLMs, right? So you ask one specific question, you're going to get different responses. The concept is the same thing, but it's going to answer you differently, right? Because there's no unique way of answering one question, right? So what comes out of it, like the completion is not unique, right? So is random actually, right? So that x t plus 1 to t, this is a random thing, and y, which I'm extracting out of it, is again a random thing, right? The answer that the language model is giving to my question is random. I mean, it's always answering my question, but it could give different ways, right? Die Sonne scheint is the classic translation. Maybe it wants to be a bit more, poetic. It would say, oh, shine die Sonne, right? It's still saying the same thing, but it just changes the order, right? So it might be the case that you get different outputs. So this means that y, given that x is a random thing, and it's again describing a distribution, right? And that distribution is somehow enforced by the distribution of your language model, right? So this is what I'm showing by q hat w here. So q hat w, this is the approximation of the distribution of y given your query. So I just asked the question. This is the distribution of the response I'm getting after decoding whatever the language model has given me. And there is no reason that this is exactly the distribution that I'm looking for, right? If I am lucky, if everything works perfect, then these two things are exactly the same thing, right? If they are not, if I'm not lucky, then they are to be different, right? In practice, they're always different, but what I hope is that I do all that encoding and decoding in a way that this approximation is quite exact. Everybody's clear? Questions? Yeah.
Like, do you think even the modern LLMs, to some degree, they're inefficient, like kind of primitive in a way? Like, just imagine we are highly dependent on a decoder to extract information from a completed text.
Yeah, actually, I mean, nowadays LLMs, they are not sensitive to that one. So this is what I'm going to explain in the next slide.
Reasoning models don't function the same way.
I mean, the encoding and decoding are so intuitive that essentially you would never rephrase your question to ChatGPT nowadays, right? So it's totally insensitive nowadays. But what you say was correct when it was like GPT-2 or 3. You're right. At that point of time, it was really important how you design this encoding and decoding. Nowadays, no. But at that point, like, it was not efficient. Yes, definitely.
GPT-4, even though it has the zero-shot learning.
Yeah, it has. It has.
So it works the same way, right?
It works the same way, but the point is that designing those functions is the question here, right? Yeah. So the only challenge for you is to design those functions. And then at some point, you needed to just go ahead and just do engineering to find the right function, or even you do training. But nowadays, that function could be as easy as what I gave you as example. Translate to German, double dot, put the English sentence, right? It's natural. It's a kind of, and this model is not sensitive to that anymore, right? So you even say, convert to German, yeah? Or even you just write it down with a very poor English. It's going to do it, right? So it's not sensitive anymore to your prompting. But early versions, they were, yes.
So, follow-up question. It is not sensitive to my prompting. The pro is that it will not get, nudged in the wrong direction. But the con of that can be that if I'm giving something highly specific, it will still generalize that?
I mean, the questions are quite different, right? So making it good in one specific task, or say some generic tasks, it doesn't say necessarily that to what extent it can generalize to every particular task. Yeah, so these are two different questions, even though, I mean, intuitively they should be related. But, I mean, usually people investigate them independently.
Like you said, right, like wrong, I say, syntax of my grammar is incorrect, and I say
yes.
something to it.
Yeah.
It'll annotate it and it'll give me the right response.
Yes.
But from that, it also tells you that even if I'm asking for something else, it might, nudge it back into,
yes, but the point is that, as I said, again, this totally depends on what happens inside your model. Because you might think, the reason that you think like this is because you compare the previous model and the new model, assuming they are actually working in the same dimensional space when they are doing embedding. But this is not the case, right? So the point is that, like, you are getting less sensitive because all of those kind of prompts that you're doing are essentially shooting points in the embedding space, which are collecting in the same point, right? Now, you want to just make it different from any other task, then you need to have enough space in your embedding space that any other kind of wrong prompt for your task is distinguished, right? So when you increase the size of your embedding space, then you are getting exponentially large in that respect, right? So as I said, these are a bit different, but definitely they are related. But people study them differently. Yeah. No worries. You had a question, yeah.
So in this case, like, when we talk about prompt design, we usually have the assumption that we're working with inference, right?
Prompt design, we're thinking of doing inference, yes, but I mean, even if you are doing generation, you can think of Q to be the autoregressive generation, right?
Right. So in this case, like the red Q, right? The red Q distribution, would that be like something that we kind of sort of expect to get out of our LLM? And
it depends. If you're thinking about, I mean, we have not talked about images yet, right? We're just talking about text. If you think about image classification, then your class is essentially specified, right? Deterministic. This is an image of a cat, right? But Y could be answered to a question, right? So I ask you one question, and then the answer is pretty much clear for that question, right? But you can give it in different ways. And all of those ways are accepted way of saying the answer, right? And because of that, you have a kind of distribution over your answers, right? And what you want to do, like I asked you, what is the color of an apple, right? And then you can tell me it's red, it's yellow, it's green, but you wouldn't say it's black, right? Yeah, right? So now, if I ask you, probably most of the time you are going to say red, so it has higher probability. But you might say it's yellow, is the lower, green is less, right? But I don't know, purple, nobody gonna say. The probability is 0, right? You get the idea, right? So this is the point that I'm making. So with that, by that distribution, I simply mean that.
Okay, but then like we have the Q hat, right? So essentially, are we trying to say that
Q hat is what, like say, in the dummy example I gave you, say 50% of the time people say red, 30% of the time they say yellow, 20% they say green, right? And they would never say anything else, right? But then when you ask your language model, it doesn't exactly mimic this frequency. It just does it like 80% red, 10% the other cases, right? So what you expect, you expect that you get very close, right? But not that one. Yeah. So you hope that this is exactly mimicking what you're looking for, right? You got the question. Okay. So, questions? Everybody's clear? Okay, great. So now this is the idea of prompting. So I put here the intuitive because essentially it has not been defined anywhere. So this is somehow I made it up out of my understanding or the actual framework that we are developing here. Now, if you want to just think about it visually, this is your language model, and what is going to happen, you're going to prompt from it, and it's going to complete the sentence, right? And the end-to-end distribution here is specified by your language model, so this is the probability of whatever you get as the completion given your prompt from the language model, the input to the language model. And then what you want to do, you want to just design one encoding which takes your prompt, your query, U, and turn it into the input of the language model. Then in this guy goes through the language model, you get the output. And then from the output, you want to design one decoding, which just looks at that output and extracts the response that you want, right? And from this U to Y, you have essentially one distribution. That distribution exactly depends on the distribution of your language model, right? So it's a function of your language model parameters. You change the language model parameters, PW is going to change, so going to be the Q hat W, right? And what you hope that this new distribution Q hat is just mimicking as close as possible the distribution of the task that you're looking for. Everybody's clear? So one thing here, when we are talking about prompting, what are the parameters that we can design? F and G, right? So F and G, this is the key difference, right? F and G are the things that you can design in this case. And when you're talking about fine-tuning, you're essentially playing around with this W, right? So this is the key difference here. Now, people, when they started with with this idea of prompting, so they were essentially initially doing prompt engineering. And by prompt engineering means exactly what we did in our example. So you just come up with one encoding function and decoding function, which exactly tells you how you can connect the input that you want to the label that you're looking for, right? And then you always use this encoding and decoding. This is engineering, right? You find the function. This was okay, but in especially earlier language models, people saw that this can go to some extent, right? And then here it comes the question. When you want to design a function which is like unclear to you what is the right choice, what should you do if you don't know what is the right choice? Is engineering the solution? No. So what do we do really in practice? Why we are here in this lecture hall? We always do learning, right? So we're going to look at examples, and then we try to learn what is the right function, right? This is how we do in machine learning. So people started to say, why should we think of f and g to be some engineered function? Well, maybe we can think of them again as neural networks, right? So f is a neural network, g is a neural network. They're going to get the prompt, they convert it to the encoded one. They get the output, they convert it to the response, and then we just train these models, right? So we're going to collect a bunch of answers. We just send the question, we get a response. We see it is not the right response that we want, so we compute a gradient, we pass it backward, right? And we change this alpha and beta, right? We keep on doing it till we get into the right encoding and decoding function. The cool thing about this is that it's going to just boost your performance, right? Because there are definitely some functions which are totally making sense for your language model, but they are not making sense to you because they are not natural, right? So they are just working with embeddings. You don't understand why should they be here, but they are not intuitive, but they are very well suited for your language model. This was the idea that people called it prompt tuning. There is a tiny bit of literature on that, so people at some point started to compute gradient to just find the right prompting. But the point here is that, as I said, like nowadays, language models are so strong in terms of completing or in terms of doing multiple tasks that you really don't need to do it, at least for simple tasks anymore. So either of them you do. So this is prompt engineering. Probably you have heard of it quite frequently. And prompt tuning is a bit of more advanced idea of the same thing. One thing you should pay attention here, when we are doing prompt tuning, like we are computing gradient, we are mathematically again doing fine-tuning, right? Because at the end of the day, I get the language model. Just look at this diagram here. I keep this guy fixed, but now I add parameters here, right? And for me, the model is again from here going towards the language model and the output, right? So the end-to-end model is again getting fine-tuned, but it's a kind of very selective fine-tuning where I keep this guy frozen and I'm just fine-tuning these two modules, right? So it's again a kind of fine-tuning, but people like to call it prompt tuning, and the main reason was that the language model was kept untouched, right? So it's still doing the job it used to do, but now you're just finding the right choice of encoding and decoding for it, for any specific task, right? So now, as I said, at the time of GPT-2, they saw that prompt design, you need to do very accurate prompt design. So you have a question? Yes? No, it's okay. Just go ahead.
So previous page.
Yes.
So two questions. One, prompt tuning, if you consider the original LLM as a linear transformation, then this is just another LoRa, right?
Is it another, not LoRa, it's the kind of, why you say LoRa?
Like essentially, given that F and G are linear transformations, right?
F and G are linear.
They are two matrices, and you have a big matrices in the middle. So basically just two LoRa, right? You just add two LoRa layers.
Yeah, but you're not adding them, right? You're not adding them up. I mean, this guy cannot be a linear transform, right? Because at the end, you want to select, collect a few tokens. So at the end of the day, you definitely have a nonlinear layer here. I get your point, but these are not simply adding up with the language model, right? Because you're in LoRa, you get the big matrix, you keep it fixed, and then you add a bunch of extra parameters to it, right? But you are not doing it here. You're cascading models, right? But if you mean it's a kind of selective fine-tuning, you're right. This is definitely a selective fine-tuning. It's in a kind of specific kind of selective fine-tuning, right? Okay. So you had another question?
Another question is, how do we actually compute the loss here, given we don't even know the answer?
Yeah, I mean, the point is that, I mean, if you just, again here, this is why I said, like, this is similar to the fine-tuning, because you need to have some reference, right? So reference could be a bunch of sample answers, or it could be human feedback, right? The human feedback would say, no, this is wrong, answer, then you're going to just compute a big loss, and then you compute the gradient, right? So now, as I said initially, with the start of GPT-2, at that point, like people find as zero-shot learning, few-shot learning, these kind of prompt design approaches are a kind of good evaluation metrics, but at the end of the day, we really need to always fine-tune it for specific tasks. And somehow, at the point, like when GPT-3 came out, people started to see that, well, this model is getting more robust against prompt design. Like, you just give a natural prompt to it, so you just say translate to a language, then it starts to translate. The point was that it's not as sensitive as we had it before, and this is the point where people started to say, okay, maybe few-shot or zero-shot learning are really a thing. We can achieve it. And if you look at the title of the paper GPT-3, it says language models are few-shot learner. And then essentially what they are saying, they say like, for few-shot learning, we have no problem anymore. I mean, you just ask your question in a very natural way by giving a bunch of examples, it's going to answer your question. You just give the task by a bunch of examples, and you're going to do it. So here was the point that people started to get more hope into it, and probably this is the time when most of us started to hear about ChatGPT, right? So ChatGPT was now a thing, like go and ask your question from ChatGPT and so on. And nowadays, things like GPT-4 are essentially zero-shot learner, so you really don't need to give examples even to it. It can simply just look at your the task that you're providing, and as long as it's a natural task, it can do it. Okay. So when this happened, people started to come up with the idea of foundation model. So they started to define a term which is foundation model. And what was the idea? They say, okay, we have these large language models, and they are capable of just mimicking a generic language distribution. And this generic language distribution is not simply just making a coherent sentence, but it's actually storing some sort of knowledge in it, right? Because it starts to not only complete the sentence, but understand what the sentence is looking for. And based on the data it has seen, it finds the right answer to that question, for instance, right? So it's a kind of intelligent action that it's doing. It is getting less and less dependent on the kind of task we are asking. So if we ask, just do a classification for me, then it does it, right? Just check the similarity, it's going to check. Complete the text, it's going to check. Answer my question, it's going to do, right? So the point was that, okay, whatever we have done before, like in old days, we used to have one specific model which does the classification for us, right? And now if we want to do similarity check, we need to develop a new deep model to do that for us, and so on. Maybe there exists one model, something like a superhero person in the world of language models, who is able to do whatever we ask, right? And then we get rid of training different models. We just train one foundation model, and this guy is able to do any task that we want to do, right? So this was the idea of foundation model. It doesn't have a very concrete definition. It's a kind of term being coined by people working on it. But the intuitive idea behind foundation model is that we are looking actually for one particular model, something like large language model, which is adaptable. It means that either you can do fine-tuning with a few data samples, or you just do a right prompt designing to a very wide range of tasks that you are looking for. So if you want to put it in our formulation, it means that whatever this task-specific distribution is, you can always come up with one either fine-tuning or prompting approach that you can somehow make the distribution of this model to mimic that distribution, right? And it's a kind of, say intuitive and at the same time idealistic kind of idea that if we can really realize it, then it essentially means that we don't need any other model, right? So whatever task we have, we just throw it on the language model, on the foundation model, and it's going to just give us whatever we need, right? So The term was coined by the Center of Research on Foundation Model. This is a center at Stanford University. I put you the link. You can take a look at them. They release reports every couple of some time to time, and then you can take a look what they are looking for, what are the achievements, what are the goals, and things like this. It's going to give you, I mean, given your knowledge right now, you do get a very clear understanding on what they are looking for. Okay, so that being said, this is finishing this chapter. What we did in this chapter, we just worked with text. And as I said initially, text is an easy kind of data because, as you saw, we could simply intuitively represent everything, right? Every part of the sentence, every word, or I don't know, every character is going to be one token, and then you have a sequence of tokens. And these sequence of tokens have a kind of relation with each other, right? They carry some context information in them, and we always need to just design a model which extract that context, and out of that context somehow predict what's coming next, right? And it's able now to generate whatever we want, right? But this is not the only kind of data that we are looking for, right? If, for instance, we really want to realize one foundation model, then essentially we need to be able to work with other modalities as well, right? So we need to be able to generate images or give image as input to our model and then take some text kind data out of it, right? So we really need a model which is able to work with any kind of, any nature, any data coming from any resource, right? And this is what we are going to do in the rest of this semester. We are going to look at what we are going to generate to be a general mathematical object, right? It could be an image, a tensor. It could be a text, a sequence of tokens. It could be a video, anything, right? And then what we want to do, we want to just pretty much extend whatever we have done in this first chapter to those modalities, right? But it's not always as easy as the language to generate those kind of modalities. So we're going to see, this is why we have the whole semester for that. We're going to see that how we can actually formulate this problem in the generic form, and then we're going to go over a few ideas which are actually completing or what we need to just generate all the modalities. So any question on this chapter?